right, so I want to introduce some of the ideas that we're going to look at in Chapter 10 today. Chapter 10, the title of the chapter is Fixed Axis Rotation. Makes it sound very intriguing. But to think about the bigger picture, we're starting to look at rigid body motion. So what do we mean when we are saying rigid body motion? Well, you might not have really given it a lot of thought, but up until now, when we treated an object moving, we really treated it like it was acting as a particle. So even though we were talking about a box sliding down an inclined plane or a ball flying through the air, in a way we just always were sort of treating those objects as they were a mass concentrated at a single location and moving along. Another word for the type of motion that we were studying would be translational motion, because it's just involving moving in 1, 2, or 3 dimensions, nothing more fancy than that. Now, as we start to look at rigid bodies, we're really dealing with the fact that we cannot treat them like just a little sphere located at a certain point. We can't treat them like a point particle. These are objects that have definite shapes, like a fan, where there's mass distributed different ways, you know, like the blades of the fan, or we have a bicycle wheel where a lot of the mass is out towards the edge of the wheel itself. In both of these cases, these are objects that do undergo fixed axis rotation. The fan blades do rotate about an axis that passes through the center, and so does the bicycle wheel. It passes through an axis. The axis passes through the center, and the wheel's rotating about that axis. So that is really the motion we're going to concentrate on in this chapter. So for right now, our objects basically are just sitting there, but they are going to be rotating about an axis. What we mean by fixed axis rotation is that that axis is not moving. So if we are talking about a bicycle wheel, the bicycle wheel actually isn't rolling along with the bicycle, but it's just sitting there. The fan's a little easier to imagine because the fan not going anywhere. Oh, and it's not oscillating. We're keeping it simple. So when we talk about that kind of motion, we want to define new quantities. And so in this picture right here, we have a very amorphous type object. It doesn't have any definite shape, but it is rotating about the origin. So the axis is passing through point O. The axis would be perpendicular to the plane of the screen. And the whole thing is rotating about that axis. So notice some of the quantities that are labeled here in this picture. For one, like, how do we measure distance or displacement? So we notice that when you look at the x-axis here, and we look, if we're following point P would move from the x-axis to up where it is as the object rotates. In that amount of time, the displacement of the entire object is going to be measured by the angle theta that it has turned through. So that's the first thing for us to realize, is theta is equal to the displacement. So that is how we're going to measure its angular displacement. And so that's another thing to think about or to notice is now when we're talking about rotation, things are going to be measured as angular quantities. So our displacement is theta. Our velocity, which is going to be the derivative of the displacement with respect to time, we call omega. And that is the angular velocity. So you can see that in this picture, omega is indicated. It's showing you the direction that it's rotating in. So as we're looking at it, it's rotating in a counterclockwise way. That's the preferred way. We'll talk about that kind of thing as we get into class. Notice that omega is shown in those arrows on the two opposite sides of the circular path. Now notice the dotted line, that's the circle, would be the path that point P would take as the object was rotating. And so we're going to notice that omega is shown on two different sides of that circle. Now, it turns out that omega is a vector, and we are going to have to find a better way to talk about the direction of omega, but we'll do that in class. In any case, first, these are our two quantities that we're defining, and so then finally, we want to talk about angular acceleration, which is going to be the derivative of omega with respect to t, which is also going to be the second derivative of theta with respect to t, and we're going to call that the angular velocity. So those are the types of terms that we're going to be using to describe things. Of course, the angular acceleration is going to happen if the angular velocity isn't constant. And notice these are all Greek letters. This is not a W. That kind of thing is my pet peeve. It's an omega. It's a Greek letter. So we always draw it like a little curvy W. And so these are some of the quantities that we're going to be looking at as we venture into rigid body motion. So in my next video, I'm going to talk about a special case where the angular acceleration is constant, and we're going to look at the equations that we come up with. And you're going to see that those are kind of